The final goal of our case study is to analyze the electricity price markets of Spain, Portugal, and Greece. In this learning unit, I will show an example of the similar analysis, but for the case of the Germany, which is an example of the Central Western Europe market, while Greece is an example of Southeastern Europe market, and Spain and Portugal together form an Iberian Peninsula market. We have our data for the German electricity prices in the file of the CSV format. Basically, the data looks like this. In order to be able to operate with this data in our Jupyter notebook, we will use the library, the Pandas library, which is the special library for data analysis. So I import it here. This library has a special function for reading the files of the CSV format, which has a name read CSV. So now we can read our CSV file, and we get this form of the data frame. So we have the index column here in bold. In our case, in our current case, the index is just the ordinal number for a row. We have in the third column price of the electricity, and in the column date time we have the time stamp corresponding to the price. Also, we can notice that for every day, for each day, we have 24 hours with the 24 corresponding prices. In order to operate with our data in a more convenient way, we will set as an index of the data frame the column datetime. Again, we have a special function in the Pandas library to do so. So now we can see that we have only two columns, one of which is index, the date time. Finally, we can check the data types of our data frame. So we can see that the column price is a float number, and our current index has a data type of an object, which is very abstract. We would like to operate with our index as with the timestamp, with a date time type. So here we set the date type of our index to the date time type. After doing this, we again have the same form of the data frame, but now our index is a date time index with a date time data type. So our data frame of our initial data is now ready to be analyzed. The next thing we will do is we plot this data simply using the plot function of the data frame library. Here in the brackets I just have set the size of our plot. So our overall initial data looks like this. So we can see, like, the first thing that we can see is that the German electricity price market has a feature of negative prices. So the market allows negative prices. In order to compare the dynamics, the tendency of electricity prices, we will plot the electricity prices data for each year and we will compare them. So in order to do this, we need to take from our initial data the data with the index corresponding to the one particular year, and then we plot this data, and we do it for every year from 2015 to year 2021, and we can then see how the data looks like. So the first thing we can notice is that we have the seasonality of the prices throughout the year, and this seasonality is weekly seasonality. Again, in order to better see the tendency, we could also consider the daily average prices, because now for each day we have 24 values of prices. We can simply take the average and again to plot this data for every year. And finally, we can also consider the daily averages for the whole time interval we have from the year 2015 to the year 2021. So our main conclusions are that the German electricity price market allows negative prices, and that we definitely have a seasonality, which is the weekly seasonality. The next thing we consider is the summary statistics. So we calculate average, standard deviation, skewness, and kurtosis for each year and for the whole period. The result is our new data frame. So from our historical data, we see that the electricity market is positively skewed. I remember that the skewness for a normal distribution is 0, and it has heavy tails, basically from the high kurtosis. So our data is not normal. And also we can see that our average are changing from one year to another, especially with the year 2021, where the value is almost 3 times higher. Also, we can plot the histogram of prices on this picture, from which we also can observe the normality of data. And finally, we can check our observations with normalities test, for example, with Shapiro-Wilk test. So the Shapiro-Wilk test tests the null hypothesis that the data was drawn from a normal distribution. So we use the function Shapiro from the scipy.stats library for our German daily data, and we see that our sample does not look Gaussian. And also we can check the same with the normal test function from the same library, which is based on the Gastino and Pearson's tests. Next, we consider the weekly pattern. In order to do this, we create the new data frame consisting of 4 columns: date, time, price, and the weekday. So in order to do this, we simply extract the date and time from the index of our data frame, and in order to assign the weekday, we use the function dayname with respect to the index. Then we plot the new averages with respect to the day of the week. So for each day of the week, Monday, Tuesday, Wednesday, and so on, and for each hour of the day, we plot the average price. So we can see that the pattern throughout the day is the same for every day of the week. So we have two peaks, two positive peaks. The first positive peak corresponds to the hour, to the 8 p.m., 8 or 9 p.m., and the second positive peak corresponds to the 7 or 8 p.m., and we have the negative peak, which corresponds to the 2 p.m. time. And also, so in red here we have the Sunday, in gray we have Saturday. We can see that the price during the working days is higher than the price during the weekends. So the price for the Saturday and Sunday is much lower than the price for the Monday, Tuesday, Wednesday, Thursday, and Friday. So as we know, time series consists of several components. So it's seasonality, which describes the periodic signal in the time series; trend, which describes whether the time series is decreasing, constant, or increasing over time; and noise, which describes what remains behind the separation of seasonality and trend from the time series. So consider the decomposition of our time series to these several components. In order to do this, we will use the Python stats models function seasonal decompose. In this function in seasonal decompose, we have to set the model. We can either set the model to be additive or multiplicative. The rule of thumb for selecting the right model is to see in our plot if the trend and seasonal variation are relatively constant over time, or in other words, linear. If yes, then we will select the additive model. Otherwise, if the trend and seasonal variation increase or decrease over time, we use multiplicative model. And so our data here are aggregated by day, and the period we want to analyze is a year, so that's why we set the period to 365. So our resulting plot is the following. Here we have again trend, seasonal component, and residuals. And we can also consider the seasonal component separately by plotting the seasonal result. And this is our yearly seasonality. The last thing that we consider for the first task is the stationarity of our time series. So we will use this function ADF test, which takes as the parameters the time series itself and the data description in the string format. The test itself is augmented Dickey-Fuller test taken from the stats models library. And also our function prints the null hypothesis, which is time series is not stationary, test statistics, p-value, and critical values for 1%, 5%, and 10%. So if we call this function with our daily data, we get that our test statistics is positive, so our daily prices is not stationary. However, if we take the difference of our daily data, we get very negative statistics and stationary time series. Now we can move on to the second task, to the choice of model and forecasting, but firstly a couple of words about data transformation. Usually, a lower variation or less spiky behavior allows us to have more accurate predictions. So, since in our case our prices have a high volatility and exhibit a price spikes, the data could be transformed, firstly. And in our case, again, since German market allows negative prices, the usual standard logarithmic transformation is not enough, and we could use more complex transformations such as, for example, area hyperbolic sine transformation. Here, further, I will not use any transformations for the sake of simplicity. The next step would be the right choice of a model. So suppose we have decided to model our time series with the Arima type model. Arima model is the autoregressive integrated moving average model, and it has three parameters, P, D, and Q. The parameter P corresponds to the autoregressive part, in particular to the non-seasonal autoregression order. And this parameter can be selected based on significant spikes from the partial autocorrelation function plot. Parameter Q corresponds to the moving average part, in particular to the number of lagged forecast errors in the prediction equation. This parameter could be selected from autocorrelation function plot if this plot has a sharp cutoff after the lag Q. And finally, parameter D corresponds to the number of non-seasonal differences we need to perform in order to have this stationarity. So, for example, for our time series, in order to determine the parameter D, we consider how many times we need to difference our daily time series. So we already know that the time series itself is not stationary, but the differenced time series is stationary. So in our case, the parameter D for the Arima model should be a value of 1, at least 1. So in order to select P and Q parameters, we need to plot the autocorrelation function plot and the partial autocorrelation function plot. So we have the special functions plot ACF and plot PACF in Python. And analyzing these plots, we can make conclusions about the possible P and Q parameters. Since we have the seasonal time series, it is better to use the sarima model or seasonal Arima model. The sarima model has 7 parameters, P, D, Q as in the previous case, capital P, capital D, capital Q, and M. Parameter M indicates the seasonality of time series. Since we have weekly seasonality for the German prices, our parameter M would be equal to 7 days. Parameters capital D, capital P, and capital Q have the same meaning as in the previous case, as in the case of the simple Arima, but applying to the seasonal process. So we need to extract the seasonal component from our time series and to perform the same procedure as in the previous case. So capital D indicates the difference in order of the seasonal process, capital P indicates the autoregressive order for the seasonal component, and capital Q indicates the moving average order for the seasonal component. So for example, in order to find the parameter capital D, we need to check whether the seasonal component is stationary or not. So in our case, we have that the seasonal part is stationary. So in our case, the parameter capital D will be equal to 0. And By plotting partial autocorrelation function and autocorrelation function, we can find parameters capital P and capital Q. As we have just seen, based on the difference in partial autocorrelation function and autocorrelation function, we can make assumptions on parameters of the right model. And we can write our own functions in order to choose the model. But also we can use the built-in functions. In particular, for Python, we have auto Arima package of the PMD Arima model. Firstly, consider the Arima model without taking into account seasonality. We are calling out Arima function specifying the following parameters. We indicate our time series. We indicate the starting values for the search of the parameters P and Q. We specify the maximum possible values for the parameters P and Q. We set seasonal parameter equal to false, specifying that we do not take into account seasonality. We set the difference parameter equal to 1. We set surprise warnings parameter as true, which means that all of the warnings coming from Arima will be squelched. We set stepwise parameter as true, which means that the function will use the stepwise algorithm to identify the optimal model parameters, and the usage of this algorithm can be significantly faster than fitting all parameter combinations. We do not specify information criterion, so the function will be using by default Akaike informational criterion. And finally, we set trace as true, which means that the function will print status on the feeds. As a result, we have the list of the models of the parameters that our function has considered with the corresponding Akaike informational criterion. And finally, as a result, we have the best model, which is Arima 616 in our case, with the corresponding Akaike information criterion. Now we use the same function, but specifying the seasonality this time. So we set the seasonal parameter as true. We add capital D, which is equal to 0 in our case. I did not specify here the start capital P, start capital Q, max capital P, and the max capital Q parameters, so the function will be using the values set by default. And the function gives us the best model, which is sarima 113202 with the seasonal parameter 7 days. And the Akaike informational criterion corresponding to this model. So the detailed description of the auto Arima package can be found by the following link. Finally, we can model our time series with the parameters we have just chosen. So for Arima model, we use the package Arima. So we model our Germany daily time series with the Arima model of order 616, and we fit our model. We can also print the results, the summary of the results of this fitting, because it has some nice values, useful values. And after fitting the model, we can finally do the forecast, the prediction. So first of all, let's do the in-sample forecast. So we use the function getPrediction, and we specify the start date of for our forecast. So since we are doing the in-sample forecast, our start date is chose to be 1 year before the time series, the end of time series. We can plot the confidence interval also. And finally, on the plot we have in blue the observed, the real values from the market, and in orange we have the values of the in-sample forecast. In order to understand how good is our forecast, we can use different measures, and one of the measures of the error is the root mean square error, RMCE. It is the standard deviation of the residuals, or the standard deviation of the prediction errors. And the residuals are the measure of how far from our prediction line real data points are. So basically, the root mean square error is a measure of how spread out these residuals are. This measure should be considered in relation to the target that we are predicting for, so it cannot be compared across different domains. And it also is in the units of our initial time series, so in our case in the price units. To sum up, in given that our range of daily price is from minus 51 euros per megawatt hour to 432 euros per megawatt hour, we have the root mean square error equal to 21.7, which is plausible. Analogously, we can forecast out of sample. So in order to do the out of sample forecast, we can either specify the number of steps we need to forecast, or we can specify the start and the end date. So I put here 1 month after the end of our initial time series. Again, we can plot also the confidence interval. In blue we have the observed data, in orange we have the predicted, forecasted out of sample data. The same procedure can be performed for the sarima, seasonal Arima model. We use the package sarimax, specifying the time series, the order, the seasonal order, and fitting the model. We can again do the in-sample forecast, considering the root mean squared error, and out of sample forecast for the 1 month after the end of the time series. The third task of the case study is connected with value at risk. Value at risk is a measure of risk for potential losses within a given portfolio over a defined period of time. The goal of the calculation is to measure the greatest potential loss under normal market circumstances at a specified confidence level. So in other words, value at risk seeks to determine the probability of a certain outcome happening. Typically, a probability of 5% is most often used. So, for example, there is a 5% probability of losing a given amount of money over a specified time horizon. Calculating Value at risk is generally done through various approaches. One of the approaches is the Monte Carlo approach. The Monte Carlo approach involves developing a model for future price changes and performing multiple hypothetical simulations in the model. The intent of the Monte Carlo approach is to generate random probabilistic results in which the outcomes differ. We performed the Monte Carlo simulation for our case, so we have chosen the model in the previous step. Now we feed this model, and then the package Sarimax has the special function called simulate, which simulates a new time series following the specified model. Sarima with orders 113 and seasonal order 202 and the seasonal parameter 7 in our case. So for example, we want to, we have the electricity prices with the last value on the last day of the year 2021. And for example, we want to simulate the price starting from the first day of 2022, and we want our last value of simulation to be the 1 year after. So we need to specify the number of observations to simulate. In our case, we would like to simulate the prices for 1 year, so a total 365 observations. And the parameter anchor here corresponds to the first period for simulation. So we set up here the value end, which refers to the beginning of the simulation at the first period after the sample. So just after the last value of our initial time series. So here on the plot we can see our Germany daily prices data in orange and the new simulated trajectory for the price starting from the 1st January of 2022 and total 365 observations. The Monte Carlo approach consists in simulating a large numbers of such trajectories. So for example, we can simulate the 1,000 trajectories for the 1 month period from the 1st January of 2022 to the 1st February of 2022. So firstly, we count how many observations we have in this period, and then we plot the new trajectories here. So in order to see how the trajectories look like, we can plot only the simulated trajectories. Consider now the forward contracts. So electricity forward contracts represent the obligation to buy or sell a fixed amount of electricity at a pre-specified contract price, which is known as the forward price, and at a certain time in the future, which is called the maturity. So the payoff of such a contract is the difference between the electricity spot price at maturity and pre-specified forward price. Suppose at the day of December 31 of the year 2021, we bought a forward contract to buy 1 megawatt hour of electricity for a forward price of 200 euros per megawatt hour at the date of the 1st February of 2022. So we have the maturity of 1 month. And we are interested to know what are these 1 month 10%, 5%, and 1% values at risk. So, value at risk is the measure of the risk of loss. It estimates how much a set of investments might lose. So we are actually interested in the profit and loss function, which is used to understand if we face a profit or a loss, in our case in a long position of a forward contract. So, for example, 5% value at risk is defined such that the probability of a loss greater than value at risk is at most 5%, while the probability of a loss less than value at risk is at least 95%. In other words, when we want to know the 5% value at risk for a forward contract, it means that we want to find the 5% of the distribution of the profit and loss function from the right, or equivalently 95% of distribution of the profit and loss functions from the left. So our goal now is to build the probability distribution of the profit and loss function. Using the Monte Carlo approach, we simulate 10,000 trajectories of electricity prices. So we have simulated the prices for 1 month. We take only the last value corresponding to the day, to the 1st February of 2022. We put these values in the separate list and convert this list to an array for the convenience. So now we have a set of the values of the possible prices at the day of the 1st February of 2022, which we obtained by the Monte Carlo simulation. So then we need to calculate the profit and loss function, which in our case is simply equals to the payoff. So we have the set of values corresponding to the profit and loss functions now. And we can build the probability distribution and plot it using the histogram function of Python. So this is our profit and loss distribution. So as I said before, in order to obtain 5% value at risk, we need either to take the 5% of this distribution from the right or 95% of this distribution from the left. In order to do this, we just need to take the quantile, 95% quantile of this distribution. And our value at risk corresponding to the 5% equals to the 39.9. This means that there is a 95% confidence that over the next month our portfolio will not lose more than 39.9 euros, or equivalently, there is only 5% chance that our loss will be larger than 39.9 euros. And the same we can do for the 10% value at risk and 1% value at risk. This was the last task of the case study, and I would like to sum up all we did before. So we have analyzed the German electricity prices market. We explored the seasonality and other features of it. We chose the right parameters for the Arima and sarima models and made the forecasts. I would like here to mention again that in order to get better forecast results, it is better to use the transformation of time series. For example, if we do not have negative prices, the logarithm transformation is enough. And in general, the electricity prices have a complex seasonality, not only weekly but also yearly. And for such a complex seasonality, sarima may be not the best solution. So there are other possible models, such as jump models or some advanced machine learning models. Plus, we can use the exogenous variables as well. So this was the very simple but very representative case. And finally, we have performed the Monte Carlo simulation, and we have calculated the value at risk for the specified particular portfolio. And the case study consists of exploring Greece and the Spanish and Portuguese markets to compare them. Are they similar, or maybe there are some major differences between them? And finally, to perform the similar analysis as we did for the case of Germany. Thank you for your attention.